Hello, welcome back. All right, this is the second half of section 9. And we're going to talk about something really important and I think super cool, which is we're going to talk about the large scale behavior of the maximum likelihood estimators. And the way we're going to do this is we are going to take apart a likelihood function and look at its pieces. Now, we couldn't do this until now because we had no idea what the information was. And we're going to Taylor series expand something. So we're going to end up with first and second derivatives. And we're going to need to know what these things are. So we just learned that you can approximate the variance of the first derivative of the log likelihood function, right? Which is the variance of the score function with the second derivative of the score function under certain circumstances. And so that'll turn out to be useful. I think before we start this, I need to talk about why. Who cares? Who cares? And the answer is you do. And you say, nah, that's not true. But it is true. It's true if you want to do inference on the maximum likelihood estimator. So now you know how to get the maximum likelihood estimator, which we've been calling theta hat n. But then what? Can you do a hypothesis test? Can you do a confidence interval? Can you do a hypothesis test? Can you get a p-value? In order to do that, you need to know what the sampling, what's the distribution of the MLE. It turns out it's almost always normal, approximately normal in large samples. Well, how can that be true for all models everywhere? Well, this is the cool thing. It turns out that it is. And so again, it's an approximation, and we'll talk about what the parameters of that approximation is. So I have a bunch of data, same setup. They're from my working model as F. They're independent and identically distributed. The maximum likelihood estimator of theta is this standard notation that I've been using. And of course, we're going to need the log density because I'm going to sum these up to get the log likelihood. So I'm going to write that as little l, or just plain old little l by itself for short. And there's some general notation that I think is helpful. The log likelihood based on n observations is this. The first derivative of the log likelihood based on n observations is this. That's the second part. And then the second derivative of the log likelihood is this guy here. And so we've been dealing and talking about these things. We've been trying to figure out what they are. And we've been seeing what they are. This, of course, is basically the first derivative of the log likelihood is the score function. And then the second derivative is related to the variance. And one way to think about this is if, in fact, you had a likelihood function here, right where this thing is flat is where you get the MLE. But the curvature of this thing right here helps determine how much information you have. That curvature is given by this second derivative piece right here. That's telling you about the curvature right here. And that curvature, if it's really narrow, means that you have a likelihood function that looks like this, right? So you have a lot of information, high curvature, high information. If you don't have a lot of curvature, you're very flat. And so your likelihood may look something like that. All right, so what am I going to do? Well, I want to understand basically this quantity right here. This quantity right here, sorry. This quantity is the score function. That's the score function based on n observations at the MLE, right? The score function at the MLE has to be 0. This is the same as that we've written, score function of x theta hat n equals 0. These are the same statements. So I'm going to take this score function, and the score function, when I evaluate it at the MLE, I get exactly 0, but the MLE is probably not the true parameter. So I'm interested in what happens to the score function at the true parameter value theta. That's what I want to know. Well, okay, let's start with what we have. We know that the score function is equal to 0. We're good. And then I'm gonna do a little Taylor series approximation. I'm going to do the Taylor expansion of the score function around this guy here. So I get this guy plus how far off times the derivative of the score function, right? Because I started with the score. So it's the derivative, which is the second derivative of the log likelihood, which is that plus I get some remainder. Now, and for Taylor series expansion, there's a whole bunch of pieces here. It would be theta hat n minus theta over 2, right, times now what would be the second derivative of the score function. The score function is already the first derivative, so then it would be the third derivative, blah, 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 blah. Essentially, we're not going to worry about the behavior. These things all get small, so we're just going to assume they go to 0. Okay, well, if they go to 0, then what I'm left with is this piece of the equation is equal to 0, or approximately equal to 0. So I get L prime n plus theta hat n minus theta. I'm just rewriting this thing. L double prime n is approximately 0. Well, what I can do is I can swing this guy over to this side and divide through by there. And that's what this is. Okay, so now I have the MLE minus the truth, how far you are away from the truth, is roughly equal to this ratio. And what I'm going to do is nothing's moving here. Like this is based on a sum, and this is based on a sum, right? Because L prime n is equal to the sum. Oh, here it is all up here. It's the sum of the individual ones. It's the sum of the score functions. So it's the sum of the score functions here. So I don't want to let that thing grow unbounded either. So I'd like to scale it. So what I'm going to do is I'm going to multiply both sides of the equation by root n. Really? How do I get that? Well, 1 over root n divided by 1 over n turns out to be root n. See that? That's so cool because this guy comes up here and that's how you get a root n. So I'm going to take 1 over the square root of n on the top. And I'm going to take 1 over the square, 1 over n times the bottom piece. And both those are going to equal to this first piece here. And we're going to say it's approximately equal. Now, each of these pieces will do something. So it turns out that the red piece, what's easiest to do here? I think actually the purple, even though it's second, is easiest to do. This is an average. This purple part's an average. This guy's an average. So by the law of large numbers, that thing's going to converge to its expected value, which turns out to be the information because that's just the second derivative. That's just what we proved, right? We proved that the expected value of the partial squared log f partial squared theta is equal to the information. That's just what we did on the first half. Now, what about this top part in red? Well, I'm going to apply the central limit theorem here. I basically have here 1 over the square root of n times a summation of some variables. And I can rewrite that as by multiplying by 1 over the square root of n times n over n times the sum of the yi's. So that this would be y bar root n. So this is going to be normal by the central limit theorem. Central limit theorem will be normal, right? Just like x bar minus mu over sigma times root n is normal 0, 1. In this case, these things have mean 0, and the variance I'm just throwing on over to that side. So this thing here, oops, and actually let me do red. So this thing here, which is this thing, that's all, I just wrote that exactly out that way, goes to a normal distribution with mean 0 and variance I theta. So what I basically have is I have now this top piece here. I basically have a normal 0. I'm just going to call it V for variance. Actually, I'm going to call it I, normal 0 I, all over, right? Well, the bottom piece goes to I. Actually, so let's see. And so the bottom piece goes to I, so it's going to be all over I squared. And so this thing is going to be normal 0 I, 1 over I. The way to see this is that, let's see, how about, okay, let me think a clearer way to do this. Let's find some room to write down here. Let's not worry about that. And then let's try it again. So I have 1 over the square root of n, L prime n theta, over minus 1 over n, L double prime n theta. So the bottom, this is going to converge in probability to a constant I theta. And the top, this is going to converge to a normal theta with the variance of I theta. So this is essentially looking like if you had 1 over a constant times a standard normal z, right? This would be a normal 0, 1 over c squared, because z is normal 0, 1. That's what you have here. And so that's why combined, these things go to normal 0, 1 over I, 1 over I. Whoops, just 1 over 1I. Excuse me. And then, of course, the front piece is this green piece right here. This is this green piece. So that's what we have. All right, let's look at this on the next page. This gives us the distribution of the maximum likelihood estimates. So now, if I move the variance to the other side, I have something super important and super common in the statistics literature, and actually in any literature dealing with coming up with confidence intervals, which basically says, hey, this quantity takes a standard normal distribution. This is exactly the same thing as x minus mu sigma over the square root of n, right? X bar, but I'm going to write it as root n times 1 over sigma x bar minus mu. That is the form that I have here. And in practice, we don't actually know, see, I need the true value here. I don't know that true value, so in practice, I plug in an estimate. And this works by the continuous mapping and law of large numbers, things that we don't have to worry about. And sometimes we'll see shorthand, which says, okay, the maximum likelihood estimator is asymptotically normal, it's centered at the true mean, and its variance is 1 over the estimated information. So this is going to be important because we're going to use this to do various things. In particular, we're going to come up with a confidence interval, right? So if you want to come up with a confidence interval, you would say, okay, well, I would do theta hat n plus or minus 1.96, and then 1.96 1 over ni thetas square root. That's the general formula for a confidence interval for a maximum likelihood estimate. And the reason that that's so helpful is, in fact, that this thing is actually not just for maximum likelihood estimates, right? Because maximum likelihood estimates we get as the solution to a score function. So this works for MLEs, solutions to score functions. Score functions are estimating equations. So we'll get this to solutions to estimating equations. And estimating equations are objective functions, so it'll work for solutions to objective functions. So this now gets you into the machine learning territory about, okay, I have all these parameters and I want to assess their variance and things like that. What do I need to do? You can get their variance by looking at the curvature of the function. That's what that is. That's the curvature of the function you're optimizing. And you can get that variance, and you can look at that to get its variance. And then this is the solution that you're finding, and you can put them all together. So these things are important and I think super helpful and will come up in different ways, and we'll talk about this over and over again. The one thing that I do want to make sure that you think about is, what does it mean for this to be the right target? And when you don't have the true mean, you don't have the correct model, this variance piece will be off. We'll learn how to correct that, but this piece we won't be able to correct. It'll just converge to something, and you may or may not know what it is. And we'll talk about that in the next time. All right. Thank you.